This week, we'll be taking a look at Boyle's Law and Charles' Law as our first two gas laws. Boyle's Law is the relationship between pressure and volume, and Charles' Law is the relationship between volume and temperature. Boyle's Law is the relationship between pressure and volume. Pressure 1 times volume 1 equals pressure 2 times volume 2. P1 and V1 are simply the initial conditions, where you're starting. P2 and V2 are ending conditions, where you're ending up. This is an indirect relationship, which means if one goes up, the other goes down. In Charles' law, we have a direct relationship. V1 over T1 equals V2 over T2. This is a direct relationship, which means if one goes up, the other goes down. 1 and 2 merely represent the conditions, 1 being the starting conditions, 2 being the ending conditions. When solving for any of these gas law problems, make sure your units match. We have to make sure that we have the same pressure unit on both sides of the equation, the same volume unit, and so forth, even the same temperature unit. If they're not the same, you must convert one side to the other. It doesn't matter what you convert into what, just make sure they're the same unit. Then we have an issue with temperature. Celsius is a very common and perfectly acceptable unit to use in a laboratory environment or any other environment. But when it comes down to gas laws, it becomes a real problem. You often divide by temperature in gas laws, and because 0 degrees Celsius really does exist, or negative degrees Celsius being extremely common, we can't divide by 0. That's physically impossible. And you can't have a negative value because then you'd end up with a negative pressure or negative volume. Essentially, space kind of ceases to exist. That's impossible. For this reason, we have to use the Kelvin scale, and this is the only temperature unit you will ever use in any gas law. The formula for Kelvin is actually pretty simple. Kelvin equals your Celsius degrees plus 273. The Kelvin scale, the units are the exact same size, like 1 degree Kelvin is the same size as 1 degree Celsius. It just lowers the 0 point to true absolute zero where there is no energy. And then we have STP. STP stands for Standard Temperature Impression, and this is important enough to warrant its own little note here. You will commonly see STP given to you in some problems, and that merely means that you already know the conditions that the gas is present at. Whenever you see the term STP, it always refers to 1 atmosphere or anything that equals 1 atmosphere. For example, 760 torr or millimeters of mercury, or 101.3 kilopascals. Those are all standard pressure. Standard temperature is simply 0 degrees Celsius or 273 Kelvin. They're both equal to each other. This is a shorthand way of common, almost everyday conditions. We have to often specify what a gas is at, and this is a shorthand method of conveying that information. In our first assignment for the week, we'll be looking at Boyle's Law. And Boyle's Law is a relationship between pressure and volume. Specifically, it is an inverse relationship. Here I've written out Boyle's Law, and I like to list out my units, especially when I'm first doing this. Not only is it easier for me to teach, it also lets me keep track of what I may have to all change. Within Boyle's Law, you need to make sure that all pressure units are the same and that all volume units are the same. They just have to be equal on both sides, the same unit. Let's take a look at number 1. The gas occupies a volume of 40 milliliters and a pressure of 800 milliliters of mercury. What will be the new volume if the pressure is reduced to 600 millimeters of mercury? Since I already have my problem set up, I'm going to go ahead and list out what units I currently see. Looking at problem number 1, I see that 40 milliliters sounds like the first volume, so I can go ahead and write that in. 40 milliliters. And then is also associated with 800 millimeters of mercury. That happens to be the first pressure. 800 millimeters of mercury. The problem continues. What will the new volume? So that sounds like V2, as if I don't know it. So I'll go ahead and put an unknown for V2. If the pressure is reduced to 600 millimeters of mercury, and that happens to be P2. Now that all my variables are listed and I know what I'm looking for, I can check and make sure that my units are the same. I have millimeters of mercury on both pressure, And I have milliliters on V1, so I can also safely assume that V2 will be some form of milliliter, unless the problem tells me otherwise. Now I can solve. Plugging in P1, which is 800 millimeters of mercury, multiply it by V1, which is 40 milliliters, equals P2. I know that, that's 600 millimeters of mercury, and I already verified that the units are the same. Multiply by V2, which I don't know, so I'll leave it as this variable. Now I just have to solve for V2. In this case, I divide both sides by 600 to get V2 by itself. So the final answer is 800 times 40 divided by 600 equals V2, which ends up being around 53.3 milliliters as the final volume. Now let's take a look at the second question for Boyle's law. I already have the same setup. I know it's Boyle's law, so I'm going to continue to use the same formulas as well as the same variables. Here, a gas is kept under a pressure of 30 atmospheres. Its volume is 600 milliliters. The gas is then pumped into a 2-liter tank. What is the change in pressure in millimeters of mercury? We do have to do a little bit of extra work on this one, so let's take a look and see what variables we currently know. I see 30 atmospheres, and that sounds like the starting pressure. So I'll go ahead and put that under pressure 1, 30 atmospheres. Divided by V1, which is 600 milliliters. The problem continues, and it says the gas is pumped into a 2-liter tank. That sounds like V2. 2 liters. What is the change in pressure in millimeters of mercury? Well, I don't know P2, but it does tell me that it must be in millimeters of mercury. Now, this problem requires some unit changes, and I do see a couple of issues. One of the first things I see is atmospheres versus millimeters of mercury. I have to convert atmospheres to millimeters of mercury because the problem demands that the answer is in millimeters of mercury. This is why we worked with pressure conversions last week. So we take our 30 atmospheres, and I cancel atmospheres, and I convert to millimeters of mercury. I know the conversion from last week is 1 atmosphere is 760 millimeters of mercury. Cancel atmospheres, quick multiplication, results in 22,800 millimeters of mercury as our new pressure 1. Then we see an issue with milliliters to liters. Both of these units must match. Now, it doesn't matter which one you convert to milliliters into liters or liters into milliliters, but they both must equal the same. I personally converted milliliters to liters, so I will take 600 milliliters, cancel milliliters, convert to liters, and I remember a conversion factor from the beginning of the year where I know that 1 liter is the same thing as 1,000 milliliters. 600 divided by 1,000 happens to be 0.6 liters as our new V1. Now that I have new variables for V1 and P1, I can plug them in. Pressure 1, the very first variable, is now going to be 22,800. Volume 1 will be 0.6. Pressure 2, we know that to be liters. We made no changes, so simply 2 liters. But we don't know, we knew V2, but we don't know pressure 2. We can leave that as a variable. Divide both sides by 2. Resolve the end, 22,800 times 0.6 divided by 2 ends up being with a new pressure 2 of 6,840 millimeters of mercury as our pressure 2 because we needed it in millimeters of mercury. This problem was all about making sure that our units matched. We converted atmospheres to millimeters of mercury and milliliters into liters and used those as our new pressure and volume 1. In the second assignment for this week, we'll be looking at Charles' Law. I'll be working on problems number 1 and number 2 with you. In Charles' Law, we have Volume divided by temperature equals the new volume divided by the new temperature. This is a change in relationship between volume and temperature, which is a direct relationship. If volume goes up, temperature goes up. There's one big consideration we have to think about in Charles' law, and that's temperature. 0 degrees Celsius is a real value. Negative Celsius is a real value, and they're easily measured in a laboratory or even common everyday environment. And we have a major issue in that you cannot divide by 0. And if we also divide by a negative number, you would end up with something like a negative volume. It's physically impossible. For that reason, when we work with gas laws of any kind, we must never ever use Celsius. We have to convert Celsius to the absolute Kelvin scale. Kelvin equals your Celsius degrees plus 273. This is the more correct temperature that we have to use. So in problem number 1, I have the same setup that I did for Boyles' law. I wrote down my formula, and I put down each unit I have so I can identify what I may have and what I'm missing. This allows me to keep track of my units a little bit better. The volume of a gas at 73 degrees Celsius is 500 milliliters. The temperature is raised to 127 degrees Celsius. What is the new volume? Plugging in what units we know, 73 degrees Celsius is the first temperature. 500 milliliters is the first volume. The temperature is raised to 127 degrees Celsius. That sounds like the ending temperature. What is the new volume? That sounds like the V2, which we don't know. Now we have to go through a few unit conversions before we solve on this problem here. One of the first things that I notice is that I cannot use Celsius, so we have to convert both of these into the Kelvin scale. If you take 73 degrees Celsius and you add 273 to it, you end up with the equivalent to 346 Kelvin. I do the same thing to T2. I can't use Celsius. Add 273 to it and you end up with 400 degrees Kelvin. These would be the temperatures I use in this formula. And checking for volume, I see I'm given milliliters. It doesn't specify what it would like the volume to be, so I'm going to assume it stays milliliters. Now I can plug in my numbers. Volume 1 is 500 milliliters, divided by temperature 1, 346, equals volume 2, which is an unknown. I'll leave that as a variable, divided by 400 Kelvin, my new temperature. Now I can solve for V2. You can cross multiply, you can reduce. It really doesn't matter what you choose to do. Here, solving for V2 is pretty easy. If you take 500 divided by 346, you end up with 2.06 equals V2 over 400. Multiply both sides by 400 to get rid of that denominator. And the final answer that you should end up getting is 823 milliliters is the final volume. In the second problem for Charles' law, let's take a look at number 2. I'm still going to use the same formula and the same setup for identifying variables. In problem number 2, we are asked what is the new volume of 300 milliliters of oxygen if the gas is cooled from 27 degrees to negative 33 degrees Celsius. Okay, so let's do a little bit of reading. We're looking for the initial volume. It looks like it starts at 300 milliliters. And I'm also looking for the initial temperature. And reading this, it says 27 degrees Celsius to negative 33. So that sounds like 27 degrees Celsius is the initial temperature. Volume 2, well, it clearly says in the problem we're looking for a new volume. We do not know what volume 2 is. And then we look for the ending temperature, T2, and it looks like it's negative 33 degrees Celsius. Now that I have all my known variables, I take a look at my units. Volume 1 is 300 milliliters. Volume 2 should also be milliliters. The problem doesn't tell me any other, just making sure they match. And then we have the Celsius issue. We know we can't use Celsius, we have to use Kelvin. So in both temperatures, I add 273. That means my temperature 1 is 300 Kelvin. And my temperature 2 is 240 Kelvin. With my variables known, I can plug it in and answer. Volume 1 was 300 milliliters. divided by 300 Kelvin. This would be a nice and easy problem. Volume 2 is unknown. We'll leave it as a variable. And temperature 2 is actually 240 Kelvin. Resolving this, 300 divided by 300 ends up being 1 equals volume 2 over 240. Multiply both sides by 240. And now we know that the new volume, the final volume, is 240 milliliters. Remembering our unit is V2, the new volume.